Phase relations at varying degrees of saturation. So I was asked specifically about that was problem 428. This is somewhat related, but a little bit more, dives in a little bit deeper than, there was several questions. So, in that assignment. So problem, yeah, 4.5, 4.8, 4.9, 4.11. And then we get to 4.28. All of them are somewhat similar, but it's sort of, different like little twists on each one. So you're getting repetition with phase relations, but, exposing you to different twists, different things that can be asked in a phase relations problem, right? So when you see that on an assignment, wow, there's 4 or 5 questions they're all just enough different to make you think, but they're all similar enough to make you practice. Well, that's exactly what I'm going to ask you on an exam. Okay. So this whole entire assignment is like that. Enough repetition that you're getting practice, but also enough sort of slightly different twists on each one to force you to really think and get exposed to the different issues within these kinds of problems. Okay, so keep that in mind. So if I look at specifically 428, it gives us some information. It says G sub S equals 2.68. So a sand, we're told that it's a sand. That's not super important for phase relations, but a sand with not 2.68, it says 2.66. E equals 0.6. Completely dry. W equals 0. Completely dry. Okay? It then becomes wetted by a rising groundwater table. So here's the soil. Think about it out in the field. It was completely dry. GS is 2.66, E equals 0.60. A rising groundwater table is generally something that happens very slow. So slowly that soil might become more and more wetted, more higher water content, higher degree of saturation after a little bit of time. It could take 1, 2, 3, 15 days or, weeks, depending on the soil type. This is a sand. It can happen rapidly, but it's becoming wetted. That doesn't mean it's going to change volume. And it certainly doesn't mean that the solids will change. GS will be constant the whole time. Void ratio will stay the same the whole time. There's no reason that the voids will expand, especially if it's a sand. Some clays, expansive clays, can expand as they get wet and shrink as they get dry. So there it is. Is it important that this is a sand? Actually, yeah. There will be no volume change just because it gets wet. Okay, that's sort of important. Compute the unit weight. Either set of units, I could call it gamma. What is the unit weight or weight density at different levels of saturation? A, in its original state, S equals 0. B, how about when it is 40% saturated? And C, what will be its density, total density, not dry density, total density when S is 100% completely saturated? Okay? So this is the question I was asked about. So how do we do this? Well, there's several different ways to do it, but the first thing I'm going to do is I am not going to want to think about the entire field of soil. Okay, so that is the problem statement. That's what you're given, and that is what's required. Okay, right here. Given and required. Now I'm going to do my solution. So I don't want to think about the entire field of soil. What I want to think about is one representative sample. I want to be able to think about it and picture it in my mind as if I could look at it. Let's not talk about the whole field. Let's talk about one bucket. Let's look at that soil in front of me, like one bucket. And how big is my bucket? You know what? To make it easy, I'm going to say my soil is exactly 1 cubic foot. Why am I allowed to do that? Why am I allowed to choose anything I want? Well, that's because they didn't tell you any values, any quantities of soil. How much soil is there? They didn't tell you anything. And again, I've said this before. First thing you do is draw a phase diagram. And if I have solids, water, and air, and I've got my weight of solids, weight of water, and total weight. On the other side, I've got my volume of solids and volume of voids. Of course, the voids are separated into water and air, and that is the total volume. So what I've done is said, well, they didn't give me anything. There's 8 values on the phase diagram, on the block diagram. They didn't give me any of them. If they give you even just one, then they are telling you exactly how much soil is there. But if they don't give you any, then it's just a whole field and you don't know how much it is. But you then get to choose. If this is cubic feet, I have 1.0 cubic feet of soil. And over here, let's do pounds. Okay? So, from there, you can start to move forward. All right? Let me actually, I don't know if I'm going to do this with real numbers, but from that point, knowing that I have 1 cubic feet of soil and I have a certain void ratio, and a certain GS, and initially S equals 0 and W equals 0, well, that means solids only. There is no water. Okay? So initially, 0 water. But I'll skip that for now. Here's what I'm going to do first. You may have memorized one of these little ones that I did because it's very, very helpful. I emphasized it a few times. But if the total volume is solids plus voids, and E is actually volume of voids to volume of solids, I can take that and sub it in here. Right? And then I can factor out that S. Okay, so I emphasize that this was a really good one to remember. Why am I starting here? Because I've got V and I've got E. So now I can say volume of solids equals total volume. If I take out the voids, I'm left with only the solids. So now I can have that number. Okay, I can have that number. And I don't have the numbers in front of me. I'm not going to calculate this, but now I've got volume of solids. Great. I can put that right there. Done.
Excuse me? I have
Yeah,
a question.
sure.
So if it's not given the total volume of the soil, you just assume
No,
the
no.
volume is
What
one?
I said was if none of the 8 quantities are given, then you can assume one of them.
Gotcha. Okay.
Okay? So look at the phase diagram and read the problem. The information in the problem, nothing is given that I can put on the phase diagram. None of the 8 quantities are given. That means they're only giving you ratios. They're not giving you any absolute quantities like pounds or newtons or feet or meters. Okay? So if none of them are given, then you can assume one of them. the best one to assume is always total volume. It's going to make all your calculations so much easier. Okay? So if none are given, then pick one. In this problem, none of the values, weights, masses, or volumes are given. And so I said, let's consider just 1 cubic foot of this whole field of soil. And then I'm able to move forward with some calculations. Okay? So now I started with V. I assumed that because I was able to. Now I calculated VS. Well, what else might I want? Oh, wait a second. GS is also equal to gamma S over gamma W, right? Why is that important? Well, I have VS, and therefore gamma S equals GS gamma W. Now I can get that. 2.66 times whatever is water, right? 62.43 pounds per cubic foot. So now I've got that value. But that's also equal to weight of solids over volume of solids. Another common error, watch the subscripts. Watch the subscripts on phase relations. Really important. This is gamma S. It means only the solids. And therefore, if I take the weight of the solids and the volume of solids. So with that, now, I manipulate that, and, well, I've got volume of solids, and I've got gamma S. So therefore, I can get the gamma S VS. Now I've got the weight of solids. So over on the other side. Now this number is known. Oh, wait, for S equals 0. This number is known too. This one is a 0, and this one is a 0. Okay? What else do I have? Well, I got the total volume. I got the volume of solids. Oh, I should have done the easy one here. Well, total volume is solids plus voids, and therefore voids must be total minus solids. Am I just picking these equations out of my head because I've always memorized them? No, it's on the diagram. It's conceptual. It's visual from the diagram, right? So whatever is not solid right here must be voids out of that total volume. And if saturation is 0, if there is no water, then the voids in the air are the same. And if there is no water, then the weight of solids and the total weight are the same. I now have all 8 quantities for S equals 0. All 8 quantities, right? And therefore, I can answer any question like S equals volume of water over volume of voids, right? Well, if S equals 0, then I've got all those 8 quantities. And it's asking me now for the total density. Well, what's the total weight over the total volume? Remember I said V equals 1? So now you take weight divided by 1. Total volume equals 1 unit. Either that's cubic feet or cubic meters is always going to be the easiest. So total weight divided by total volume. Now I've got what is the density when S equals 0? Okay? This is where it gets a little tricky. What about the other two? Well, you might want to remember a little trick I gave you. This one is asking you for the, 3 different cases of saturation. But there's another problem. And by the way, the Tuesday A groups, we start proctor test tomorrow, and labs 4 and 6, you have to determine in the lab how much water must be added, right? And so that's multiple cases of water content. So I talked about this briefly a couple of times, but if water content is weight of water over weight of solids, and the solids don't change, that means any change of water content comes only from the weight of water, not the weight of solids. If it's a single variable change, then they're directly related. So how much water must be added? Well, exactly this much. Key is the solids don't change. Okay, but this question doesn't ask for multiple cases of water content or changing water content. This one asks about changing saturation. Same idea. If the soil is not going to expand, the voids do not expand. If there's any change in saturation, it's only because of the water. It's only because of the water. So therefore, here's what I can do. Delta VW equals delta S VV. There's other ways to think about this and do it, but this is the easiest one, I think, for me certainly, and I think probably for most of you. And so I already know to go from 0 to 40% saturation. I already know 0. The question is, what about 40%? I already know the volume of voids, and those are not changing. So if I can say delta VW equals, well, if it ends at 40% and it started at 0 times the given volume of voids, which I already know, right? That tells me how much water is needed to make it 40% saturated. So I can get that number and go back to my phase diagram. For case A, it was 0. But for case B, it is some other value for the volume of water. And from that, with the density of water, I can get the weight of water. Weight of water for S equals 40, right? Equals, and I might call this volume of water when S equals 40. Okay, well, gamma W times VW, in this case, for S equals 40. So now I've got the volume of water, the weight of water. So I now know the volume of water and the weight of water for 40% saturation. And the solids didn't change. So I've got solids and water. I've got the total weight and the total volume. That tells me density or dry density or whatever. I have all 8 quantities so I can calculate whatever's needed. Okay? And then the same idea, really, is for S equals 100%. So VW for S equals 100% would be, well, I can go back to the beginning, or I can go with the 40%. Maybe it's better to go back to the beginning, but it doesn't really matter. 100% minus the original 0% is the change in water times the voids. What if all the voids are filled with water? Actually, that's even easier. What if all the voids are filled with water? The question is, what is the weight of water for S equals 100%? If all the voids are filled with water, VW of 100%, well, that means all the voids are filled with water. 2 numbers that you already knew, gamma W and VW. So we go back here. I now know a new value for my weight of water, and therefore the new value if it was 100% saturated for the total weight. So if I now have the new total weight and the same old volume that it's always been, I now know the density.